Hello everyone, my name is Bryant Bernhard. I am from UDINUS University. Currently, I am in my 4th semester. And today, in this video, I would like to present my biggest project so far, AI-driven liveness detection for enhanced facial recognition security. Before we get off into it, let's begin by considering fundamental questions towards our modern security system. How confident we can be that the face unlocking our phone is live? Would a high-resolution photograph or video replay successfully bypass this system? These questions highlight a critical vulnerability in facial recognition technology, known as personalization attack, or more commonly known as spoofing attack. The core problem is that the algorithm is excel at match one's identity, but properly when verifying the liveness. This creates significant gap. In this project, I address this gap by designing and evaluating an AI system that able to distinguishing a real person from the fakes. The significant gap I mentioned earlier is very critical because it addresses a fundamental trust issue in our increasingly digital world. As our identity become more integrated with technology, facial recognition has become one of the primary methods in modern security systems. It acts as the key to our financial account, to our sensitive data, even to secure physical location. Therefore, a successful spoofing attack can lead to significant consequences, ranging from direct financial loss to severe identity fraud. This vulnerability exists because of what these systems are designed to do. The facial recognition algorithms are designed to solve identity matching problem tests. Their function is to match person's identity by analyzing their geometric facial features. However, they aren't built for another crucial task, which is verifying if the face is actually belong to a real person. This creates what I call a liveness gap. Since the algorithm's only job is to match features, the system will correctly match the photo, but eventually the system will fail the security task. To close this gap, a second layer of security is required. This project has several goals to be achieved. First, and the primary goal is to develop a model with high classification accuracy. This makes the model more reliable in distinguishing real faces and common to the spoof attacks, such as images and video replay. Second, to ensure the model is robust, the model must be able to perform well under the kinds of variations seen in the real world, such as changes in lighting, camera quality, and subject position. And third, to deliver this solution more efficiently, this was achieved by leveraging the model training through transfer learning, which avoid the immense of computational cost training a model from scratch. However, there is a technical challenges that must to be faced. First is subtle feature detection. A high-quality image and video replays can present facial features that are almost identical to a real person, which make it difficult for an algorithm to find a microscopic artifact that can tell which is the fake one. Second is generalization. The model must be able to generalize from the training data to correctly identify the faces it has never seen before, and ideally, variations of spoof attacks that were not originally in training dataset. Third and finally, the common issue in such dataset is class imbalance. The number of live samples can be significantly different from the number of spoof samples. If not handled correctly, this can bias the model during the training, causing it to favor the majority class. To address these challenges, I designed and implemented a system with several key components. The process begins with an input image, which first goes into the pre-processing pipeline, having its dimension resized into the uniform dimension and being normalized, then followed by the data augmentation step. The preprocessed image then fed into the core of the system, which is efficient P2 model, which acts as the powerful feature extractor. The features then pass into the custom classifier layer, which makes the final prediction, outputting the probability of live and spoof classes. At the core of the system, we have efficient P2 model. I choose this specific architecture because of its well-documented balance of high accuracy and computational efficiency, providing better performance with fewer parameters compared to older models like VGG or ResNet. Crucially, instead of training the model from scratch, I employed transfer learning. Efficient P2 model was already pre-trained on a large-scale ImageNet dataset, which means that the model has already possessed a great understanding of general visual features like edges, patterns, and textures. My work involved on modifying the model's original top layer by adding a new small classifier layer, which then specifically trained on the spoof attacks problem task. This method is highly efficient and leverages the powerful feature extraction capabilities the model has already learned. Now we will see how the system design addresses the challenges I mentioned earlier. For the generalization challenge, I implemented a strong pipeline of data augmentation. Before being fed into the model, the training data were randomly rotated, flipped, and had their brightness altered. This exposes the model into the wide variations of conditions that it might encounter in the real world, making it more robust and avoid overfitting. And to address the challenges of class imbalance and subtle feature differentiation, I use focal loss. Unlike cross-entropy loss, focal loss dynamically reduces the weight of easy, well-classified examples. This forces the model to concentrate its efforts on the hard-to-distinguish spoof example, which is absolutely critical for achieving a high performance in this task. And to make the model more effective in practical way, I developed a simple web application using Streamlit framework. This allows us to interactively the model effectiveness on a new image it has never seen before, moving it beyond the notebook. For the term of implementation, the entire system was built in Python. I use PyTorch framework for model development and augmentation libraries for data augmentation pipeline. The model training was conducted on Kaggle platform, leveraging their cloud GPU resources for faster computation. I personally wrote approximately 600 lines of code. The code was responsible for custom data loaders and implementation of training and validation loops, and also integration of different components and libraries to a cohesive system. Now we have covered the system design, now let's examine its performance. To evaluate the model, I use a large-scale celeb-spoof dataset which contains a wide variety of subjects and a common to this spoof attack. For performance measurement, I use two key metrics. First is accuracy, which provides an overall percentage of correct prediction. Second is ROC score. This metric is essentially important for classification tasks like this. It measured how well the model in distinguishing a real person from the fixed one. Now let's see the quantitative result. On the unseen test dataset, the model successfully achieved accuracy of 86.70%. And more significantly, the model has achieved ROC score 0.9849. This score close to 1 is a strong result. This indicates that the model has acquired a great capability in distinguishing a real person from the fixed one. Now we've seen the result from the deployed application. If we take an image of a real person, the system will correctly process it and identify it as live. Conversely, if we upload a spoof attack, in this case a picture of a person, the system will correctly identify it as a threat and classify it as spoof. This demonstrates that the core logic of the system is work as intended in deployed application. Based on this result, we can perform analysis on solution strength and solution weaknesses. The primary strength of this project is the tangible proof of concept. Now we have a working application, not just a model in a notebook. This is backed by the model's high performance and high accuracy. Second is the key limitation of this project is that the application is heavily relies on static image processing. It takes the image and process it, but it doesn't get work on in a real-time video stream. In summary, the system is success to address the problem of the spoof attack in facial recognition algorithm. By implementing transfer learning with efficient P2 model and using techniques like vocal loss, we were able to build a model with a high accuracy and performance, even in a deployed application. However, there is challenges that remain unresolved. First and most significant challenge that remains unresolved is the model robustness against advanced attack. While the model is effective against 2D attacks, its performance against sophisticated 3D attacks like realistic mask is remained unknown and represent a critical area for improvement. Second, for the model more practical in the real world, it must be able to process a real-time video with a very low latency as possible, which the current version of the application is not optimized for. The limitation I mentioned earlier is naturally direct the future work. For enhance the model robustness, we need to expand dataset and model architecture. The plan is we need to add 3 spoof examples to the training dataset like realistic mask, and we need to explore a model architecture with better understanding things like depth and textures. And for real-time detection, integrating real-time video with webcam is needed. And to boost the model speed, we can perform technique like quantization to reduce the processing lag. And finally, we can do benchmarking to validate the system performance in real-time video. Thank you very much for your time. I apologize if there are any mistakes happened during the presentation. I hope this presentation has been insightful for you. Thank you very much. See you on the next time.